for part A, they want the ball's instantaneous speed 25 degrees below the initial release point. Well, since conservative system, I know that the change in PE is going to be equal to the change in KE. How do I know it's conservative? There's no other forces or factors that's going to make me lose energy outside the system. So yeah, it's conservative. So I know that this is going to be mg, change in h, which is equal to 1/2 m capital M v squared. Right? And I can do this because I know there's no initial kinetic energy, so I know that the final kinetic energy is just going to be that v I'm looking for, because there is no v to account for when the ball is held up at rest. Right? So the m is going to cancel out, and that's going to be g delta h is equal to 1/2 v squared. But how do I find delta h? Well, as we look at the diagram, it's like this, right? Where this is 25 degrees, and the ball goes from here to here, right? So how do I find that difference in height? Well, I know the length of this is 3 meters, right? So if I get the opposite of this length right here, that's going to get me the delta h right here. So that would be L sine of 25, because that's opposite. And I know L is 3 meters, but I'll put that in later. So GL sine 25 is equal to 1/2 v squared. I multiply 2 to the other side. And I square root both sides. And then I will do v is equal to the square root, and I'll plug in my variables. 9.8, 3, and sine of 25. And that comes out to be 4.98 positive, because not yet speed. And then my final answer, they want speed, so I'll just take the absolute value. That's equal to 4.98 meters per second. So this is my final answer, and that's how you calculate the speed. For the next part, they want the magnitude of the A net, right? Well, I know the total A net acceleration is going to be made up of 2 components, and that's going to be the centripetal acceleration plus the tangential acceleration. But I can't just add it up like these. These are not scalar quantities. These are vector quantities, right? So in order to combine the vector quantities, I'll need to use Pythagorean theorem. So I'm going to square and then square root everything. So that's my general expression to find A net. Now I need to find what AC is. Well, what is AC equal to? We have the formula, which is v squared over r. And my v from the previous problem, 4.98 squared over r. But what is r? Well, that's just the length of the string, 3 meters. Right, so that gets me AC. I'm just going to leave it like that, because I'll do everything in the calculator one combined step. And now I need to find A tan. Well, how do I find A tan? Well, first I'll need to look at the image, the diagram. Again, I have this rope thing right here, pendulum. Initially it was here, and now it goes down here, right? Well, what's motivating the tangential acceleration? Well, that's going to be the FGX vector, and let's visualize that. So I know FG is going to be pointing straight down, right? And I know the FGX vector is going to follow somewhat of a plane like that, right? The FGX. Let me make this longer so I can draw FGY better later. But I know this motivates the tangential acceleration, right? So I'm going to label that FGX, and that means downwards, actually, because FG is pointing downwards. This is going to motivate FGY. Now, you may be asking, why don't I need to account for FGY? Isn't this also working with the centripetal? Well, I don't need to account for it, because AC already accounts for tension from that string, and FGY, which is going against, it already accounts for all that. So yeah, I just need to look at FGX. That's an X right there, to look at my A tan. Well, what is FG, first of all? Well, FG is going to be equal to mv, right? And this FGX component, how do I know what angle to use? Well, this 25 degrees right here, right? That's just equivalent to this 25 degrees right here. It's like an incline, right? So I just need FG's adjacent, the adjacent component, right? So I can just do mg, which is equal to fg, and then take the adjacent cosine 25. And that's going to be equal to fgx. But I don't want fgx, I want A tan. Well, what do I know? F equals ma, right? So if I divide m by the force, I will get acceleration. So if I divide m on both sides, this cancels out, right? And this just turns into A tan, because it's the acceleration in the tangential direction, A tan. And that's just going to be equal to g cosine 25. Right? So now that I have those two values, I can simply just plug it in here. So I know delta A net, magnitude A net is going to be equal to square root of AC squared. Well, what was AC? 4.98 squared over 3. This all squared. Plus, well, what is A tan? G cosine 25. And that's all squared. Right? I'm just going to keep it up here. G turns into 9.8. Make that neater. Like so, 9.8 cosine 25 squared. And this is 4.98 squared over 3. And that comes out to be 12.14 meters per second squared. Alright, for part C, they want the magnitude of the angular acceleration at that position 25 degrees below the point we've been working with, right? So what this is going to equal to, well, first of all, I know that angular acceleration is equal to, actually no, I know that normal acceleration is equal to angular times r, right? Well, what is this quote-unquote normal acceleration I'm going to use? Well, it's going to be the a tan vector, not the AC vector, the a tan vector, because that a tan is our linear, and we're turning it now into rotational, angular. Okay, so what is a tan? Well, from our previous problem, a tan was equal to g cos 25, right? And g cos 25, 9.8 cos 25 simplifies to 8.88 meters per second squared, right? So now I'm just going to use this formula right here, 8.88 over r, divide r both sides to get the angular, over r, what is r? 3, is going to be equal to my angular, right? So that means angular is equal to around 2.96 rads per second squared. And magnitude, so I don't need any direction. Ooh, I didn't open it. Okay, part D. They want the magnitude of the tension in the cord at the lowest point of the swing. So there's my picture of the lowest point. Your block is here. I don't care about it. I want the tension here. So I want this tension force, right? Well, what's making up the centripetal force at this point? Well, I know that SC is going to be composed of the tension going inwards. This force going inwards needs to be prominent in order to motivate this circular motion, because if it wasn't, then how would it go in a circle? Minus FG, because I know there's going to be a weight vector, force vector of weight, right? Well, FG is equal to mg, t stays the variable we're trying to find, and FC turns into mv squared over r. Is equal to t minus mg. Right, so I'm going to do mv squared over r plus mg is equal to t. But then, what is v? Oh, wait, let's use the v from part... No, I can't use the v from part A because now it's at a lower motion. But once again, I can apply the same logic. The change in PE is equal to the change in KE, conservative system. Where this is still 1/2 mv squared, but this v is not the same now because it's for part D. And this change in PE, well, it's going to be really easy now because this change in H, now we know it's just the whole 3 meters because I don't need to find anything. It's the whole length of the string now because before you were like that and now you're down here. The whole length of the string, 3 meters. So this delta H, you know that, right? That this mg, delta H is now just going to be 3 meters is equal to 1/2 mv squared. I'm just going to cancel out the m's. So I have g times 3, that, right? I'm just going to change g to the value it is, 9.8 times 3. Multiply 2 to the other side and take the square root of that all. So square root 2gl, familiar formula, is equal to v. So therefore v is equal to square root 2 times 9.8 times l. 7.668 meters per second, positive direction, doesn't really matter. It's just going to be intermediate in my calculation. So what is m? 1.8 kilograms times 7.668 squared over 3. Pore space usage, whatever, plus 1.8 times 9.8, and that's going to be equal to t. So, sorry, that simplifies to where t is equal to 52.92 newtons. For part E, they want the speed of the steel ball after collision. Well, first of all, if I know the speed of the steel ball from the previous equation, was equal to, from the previous problem part, was equal to 7.668 meters per second, right? So then I can, since it's a collision, I can apply conservation of linear momentum. Right? Applying conservation of linear momentum, I'm going to write out the general term first. It's going to be m1 vi plus m2 vi plus all other terms necessary is going to be equal to simply m1 vf. You know, these vi, well, I could do vi1, vi2, vf1 plus m2 vf2 plus dot dot dot, right? But I don't need really any of these. I only need to look at this and that, this and that. I don't need the extra dot dot dot. So I'm going to do m1, which is 1.8 times vi1, which was right here, the speed of the steel ball before collision. And this one, the speed before collision, was 0, so I can just leave that there. And it's going to be equal to m1 times vf1, which I'm solving for, plus m2, which is 0.4, plus vf2, which I don't need to solve for, right? So how do I find this vf2? I mean, how do I find vf1, right? When I have this unknown right here, well, I'll have to apply the conservation of energy because this is an elastic collision, so I know energy is conserved. So I'm going to have 1/2 m, and then vi1 squared, so it's going to be plus, oh no, it's going to be equal to 1.8, 1/2 1.8 vf1 squared plus 1/2 1.8 vf2 squared. Right? So what do I want to do? Well, I want to turn vf2 into terms of vf1 so I can solve for vf1. Follow? So then what I'm going to do is move this to the other side and then divide by that to get vf2. So, I'm going to show that work over here really. So I know that vf2 is going to be equal to 1.8 times 7.668, which is equal to 13.8 approximately, right? Minus 1.8 vf1, and that's all over 0.4. So I'm going to plug that in over here. 13.8 minus 1.8 vf1 over 0.4. This is all going to be squared. Right? And this is going to be, no, not 1.8, 0.4. 1/2, 0.4 right here, plus 1/2, 1.8 vf1 squared. And that's going to be equal to a constant over here. Let us find that constant, 1/2 times 1.8 times 7.668 squared. That constant is going to be 52.92. Okay, so now I need to solve for vf1. To do that, I'm going to simplify the equation until I have it in forms of quad. So I'm going to have is equal to 0, and I'm going to have 1/2 1.8 vf1 squared. Right, it's going to be plus this 1/2 0.4. That's just going to change that to 0.2 to make it easier. And this right here, I'm going to have to expand this. So I will show this expansion up here. Right? It's going to be 13 minus 1.8 over 0.4, and that's going to be multiplied by itself. 13.8 minus 0.8 vf1 over 0.4. Right? And I'm just going to simplify this. 13.8 over 0.4 is going to be equal to 34.5. And the 0.4, 1.8 divided by 0.4 is going to be 4.5. And I can do the same over here. I just to simplify the division of 0.4 on the bottom, so I can expand it easier. I have 34.5 here. I'm going to have 4.5 here. Right? So now I'm going to multiply the first term. I'm going to FOIL. First, other, and last. Something like that. I'm just going to expand it. 34.5 times 34.5. It's going to be 1090.25. Right? And now that times minus 4.5. So 34.5 times 4.5. Right? I'm going to have that. I'm going to have that two of those terms. So I'm just going to multiply that by 2. So I'm going to have a minus 310.5 vf1. Right? And I'm going to have the final term, which is negative 4.5 times itself, negative 4.5. That can be equal to a positive 20.25 vf1 squared. Okay, so that's the expansion right here. So I'm really just going to have that 0.2 here, right, plus 2, yeah, plus 0.2 times whatever that is, 11190.25 minus 310.5 VF1 plus 20.25 VF1 squared. And that's all times 0.02. And don't forget this term right here. This term came over. Now I will write that term. 52.92. Okay? And I'll simplify everything. 0.2 is going to be distributed to everything. So 0.2 to that. This is going to become... Just keep this as 0.2 being distributed to everything. I'm just going to rewrite it for ease. That, right? That's 0.2 being multiplied. And now 0.2 times this coefficient right here, 310.5, is going to be 62.1. And then 0.2 times this right here, 20.25 times 0.2, and that's going to be 4.05 VF1 squared. Right, minus the 52.92. So I'm going to get that constant right here, 238.05 minus 52.92. And that is going to turn this constant right here into 185.13 as so. We have 1/2 1.8 VF1 squared plus the constant right here, that, and then I just need to add the VF squared terms. So 1/2 times 1.8 is going to be 0.9 plus 4.05. Let's get a 4.95 VF1 squared, right? Minus 62.1 VF1 plus 185.13, and that's all going to be equal to 0. So now I can apply quad and go to my programs. Quad, my A term is 4.95. My B term is negative 62.1, and my C term is 185.13, and that's going to give me two values, and I'm going to choose the lesser value because if I will check in the conservation of momentum, that's the value that will make sense. So I'm going to get VF1 is equal to 4.877 meters per second. The other value does not make sense in terms of conservation of momentum. So this is my answer, and I need to put a positive sign because it's asking for velocity. There we go. Problem F, previously the steel ball speed is 7.668 meters per second, right? So I can use that, and then the speed after collision is going to be 2VF, which is going to be VI1 and then VF1, right, after collision. I found that last, which is V4.88 meters per second. I found that in the last part, okay? So those are our known values already, right? So to find the initial speed of the second block, I can find the VF2 of the second block using conservation of linear momentum, right? PI is equal to the sum here, PF, right? And I established previously what that would look like. So I'm just going to start with my values, okay? M, VI1 is going to be 7.668 is equal to the first M of the steel ball times VF1 plus the mass of the block times VF2, right? And I'm just going to simplify that. It's going to be 1.8 times 7.668, right? And it's going to equal to 13.8024, right? And I'm going to subtract 1.8 times 4.88 from that. That gets me 5.0184 because I'm subtracted this, right? 0.784, and that's going to equal to 0.4 VF2. It's going to equal to 0.4 VF2, right? And I divide both sides by 0.4. And I get my VF2 to be equal to that divided by 0.4, which is 12.546 meters per second. Now with my VF2, I can continue this problem. Let me just clear up this one. Where, VF2 is equal to 12.546 meters per second. Okay, so this VF2 is going to be the initial speed of the block, right, before it starts moving along that horizontal pathway, right? Well, I know the horizontal pathway has friction, so it's going to slow down eventually to stop, and I need to find that time, right? So first I'm going to use, first I'm going to address actually what the friction acceleration is that slows it down. So what I'm going to do is F of k is equal to Fn, which is mg times mu k, right? But F of k is made by m and then a fric, which is equal to m and then g mu k, right? The m's will cancel out, right? So I have the a due to friction is going to be equal to g times mu k, right? So 9.8 times 0.16 is going to be equal to 1.568 meters per second squared. And I'm going to treat this negative because it works against us, okay? This is just for the sake of calculations in the future. Actually, no, I'm going to take the magnitude of that, right? Because I don't really need it, okay? So what I'm going to do now is I'm going to do VF is equal to VI minus AT, right? Now I can move VF is going to be 0 because that's when the block stops, right? So I'm going to have AT is equal to VI, right? So VI over A. So T is equal to VI over A. Simply that. So T is equal to VI over A. Well, what is VI? The speed I found after the collision. So 12.546, right? And I'm just going to divide that by A, 1.568. And that gets me 8 seconds. Okay, so I see that there's a new system now, and the horizontal length is 3/4 of the original distance. Well, to find distance, I can just do 1/2 at squared with the a fric, because I'm working backwards, right? Is equal to delta x, right? So I know my t was about 8, right? And my a was 1.568, right? So I know that 1/2 a t squared is going to be 50.176 meters, right? And now it's going to be 3/4 of the distance. So 3/4 of that will be going to be 37.632 meters. So this is going to be the new distance, right? So I can find the speed now before it hits the block, because there's going to be a new inelastic collision, right? So I can use common form to find that, because I know that vf squared minus vi squared is equal to 2a delta x, right? Well, my new distance is going to be 37.632. A is going to be 1.568. There's going to be 2 here, right? And I'm going to add, actually, the initial speed to the other side, right? And from that inelastic collision, we have the initial speed of, what was it again? Yeah, 12.546 squared, right? So I know Vf is going to be equal to the square root of all of this, because this is adding Vi squared over here, and then 2a delta x, right? So that gets my Vf to be square root of 2 times 1.568 times 37.632 plus 12.546 squared, right? So my something's wrong. Oh, right, I forgot. This has to be negative because it's working against our line of motion. In this case, we're treating it negatively now, because we're treating this as a acceleration that acts against, right? So if this is an acceleration that acts against, it needs to contribute a negative value to this Vf. Otherwise, you're going to get a value that ends up being bigger than your Vi, which makes no sense, because this friction force is acting against you now. So now I'm counting it as negative, whereas before I was just using magnitude because I simply wanted a shortcut to find time. Because negative was already accounted for in the equation where it was Vi minus At. Okay? So I'm going to actually adjust that. Negative. And that gets me the Vf to be 6.276 meters per second. So now with this Vf, to find the angular speed immediately after collision, I can use the conservation of angular momentum. So I'm going to have the Li is going to be equal to the sum of Lf, angular momentum, right? And angular momentum is just going to be Iw, but remember that we learned how to do Iw. I turned into CMR squared, and W turned into V over R squared, right? Because no, W turns into V over R, because this is just W, so this is V over R, right? One R cancels out, so I'm going to have an R here. I'm going to have an MV there, CMVR. So CPR, CMVR, okay? So I'm just going to use that to shortcut the initial before collision versus after collision, okay? So my Li, I'm going to have my CPR, my CMVR, right? Of all the objects, right? But because there's only one object in movement before the collision, right? I only need to account for the block. So I know the block is point mass, so the coefficient of inertia is going to be 1. So I just need the 0.4 of the block, right? And then I need the V, 6.276. And then I need the R, which is 2/3 of the length away from the pivot, right? So 2/3 of the length is going to be 2/3 of 5, which is going to be 10 over 3. I'm going to change that to a decimal because I hate fractions, which is going to be 3.33. So that is going to be my CMVR. That is going to be my initial angular momentum, right? And I have to equal that to the final angular momentum. So it's going to be the combined inertias, because it's inelastic. They're sticking together, right? So the combined inertia is going to be the inertia of a rod first, which is a rod attached by its end, which is the coefficient is going to be 1/3. The M of the rod is going to be 1.1 times L squared, which is going to be 5 squared. And that's going to be plus mr squared, because point mass. So 0.4 times 2/3 of L, which is going to be 3.33 again, squared, right? And that's all times the final angular after the collision, okay? Which I'll represent as Wf. So basically, I'm just going to simplify now. I'm just going to get this, and I'm going to divide it by the total inertia of the new system, the block rod system. Okay, so 0.4 times 6.276 times 3.33, and that's going to be divided by 1/3, 1.1 times 5 squared, plus 0.4 times 3.33, 2 squared. Okay, that's going to get my Wf to be equal to 0.615 about there rads per second, right? And then I'll do, well, since it's going to hit, right, and it's going to go counterclockwise, actually counterclockwise is the positive direction, but they want the angular speed, right? So I can get rid of the sign, and it's going to be 0.615 radians per second. Like so. Alright, from the previous problem, I knew the W after the collision is equal to 0.615 rads per second, right? And I'm going to use this because it wants the height which the system will rise after collision, right? So I'm going to have that, right? I know that my inertia of this system, this raw block system, was equal to 1/3 ml squared plus mr squared which is going to be the 0.4, and then R, which is 2/3 of a fifth, which is 3.33 r squared, right? And that's going to equal to, I'm just going to find a value to ease my calculations. There we go, and that's equal to 13.60 inertia, the system, so kgm squared. Okay, so that's my inertia of the system. That's the rod, right? So I'll just use the conservation of energy, right? Because the energy, the rotational energy I have before is going to translate into how high I go up. So basically, the change in rotational energy is going to be equal to the change in mgh, potential energy. So the change in rot, I'll just write rot energy. It's going to be equal to the change in PE, because how much I go up will be determined by how much energy I have to convert to PE. Okay, so I know my change in rot energy is going to be all this energy right here. So the formula is 1/2 IW squared is going to be equal to mgh, right? Change in h. I want to find that change in h, so I'll divide mg to the other side. Is equal to change in h, right? So I'm going to have delta h is going to be equal to 1/2 I, which is just 13.6, W, which was 0.615, squared over mg, where m is going to be the total mass of the system, 1.1 plus 0.4, so that was 1.5 actually, and then g is 9.8. So that gets my delta h to be equal to 1/2 13.6.615 squared over 1.5 times 9.8, 0.175 meters. And that's how high it will rise. Okay, for part I claim it will decrease. I'm going to talk you through the justification because on a AP test I would write like a few sentences or so, but for this sake of this assignment, I will just talk you through it. Okay, so when the block collides, right, it's going to be a change in momentum from the first block to this new system, right? This change in momentum can be represented as a force times delta t, otherwise known as capital I impulse, right? Now this impulse, not to confuse it with inertia, this impulse is going to be the same force over time for the system regardless of how close it is to the pivot, because m isn't changing, v isn't changing, so therefore your impulse isn't changing because it's still going to be applied for like the same amount of time because, you know, they're still going to stick together, right? So what does that establish? That f is constant. Now, this is where we bring in the idea of torque. You know that torque is equal to Fr, right? And you know that a torque applied for a certain amount of time will equal to a change in your angular momentum, right? And your angular momentum will be consisted of this new I system in W, right? With this torque exerted for an amount of time. You know the time's going to be the same logic as why time was same here with the force, right? But now we look at torque. You see torque is combined of force and R distance from pivot. You know the force is constant, right? So the only difference you have here is your R. Well, what's the difference between your R? 2/3 L was a larger value than this new L over 2, right? Which is a lesser value. That means previously this 2/3 L was applied for this amount of time. So a larger value was applied for a larger amount of time, and this I system is constant, so this W is a larger value. But now if we decrease the R, decrease the distance from the pivot, right? The torque being applied for the same amount of time is less. And if this torque being applied for the same amount of time is less, right, then W therefore is less than before, because before you have more torque. Now you have less torque. Therefore, it decreases. Finally, for part J, if they remove it, right, they want the oscillation period of this rod block system. So that will be represented by our physical pendulum formula, where T is equal to 2 pi square root I cis over M total to G, and then D, center of mass. Well, this I cis, we found it before. I cis is going to be equal to 13.6 kilograms meters square. Okay, to mR squared. Yeah, kilogram meter squared. And then this mt, simple, is going to be equal to the 1.5 kilograms because it's going to be that new rod block system. G is, our constant 9.8. And distance from the center of mass, this is the only thing we really need to think about. Okay, so you have the distance, you have the mass of the rod, right? And its center of mass is going to be halfway down, so 2.5 meters. And actually, I will write down the general formula for you. You're going to have the mass of the first object, right, times how far it is down, plus the mass of the second object, and really how far it is to its center mass over the m1 plus m2 total mass, accounting for how many other masses, how many things there are needed, right? So since there's only two, this is going to be my general form. So that means DCM is going to be equal to the m1 being 1.1 kilograms, because my m1 will be the rod in this case. That's just how I want to look at it, and that's how I'm defining it right now. So that's going to be 2.5 now, plus my m2, which is going to be 0.4, and my x2, which is going to be how far it is. It's going to go back to its original system, so it's going to be 2/3 L down, so that's 2.33. And that's over the m total, which is just 1.5. Right? All the other units will cancel out to where it's just going to be in terms of meters. So let's give you 1.1 times 2.5 plus 0.4 times 3.33 over 1.5. And that's going to be 2.721 meters. Okay? So now I just plug it into the formula. T is equal to 2 pi square root of 13.6 over m total 1.5 times 9.8 times DCM 2.721. There we go. So T is equal to, let's simplify it. .66 seconds for an oscillation period of the rod block system.